When you put together an inductor L and a capacitor C in a circuit, it turns out something pretty marvelous happens. Let's have a look. So suppose here I've got a switch that is initially closing this circuit here, and so our battery has charged up this capacitor. That'll be our initial state, time zero. This capacitor is fully charged and there's no current in this loop. And then at time zero, we're going to throw this switch to remove the battery from our circuit and just connect up our capacitor to this inductor over here in this loop. And we'll assume the ideal case in which there is no resistance anywhere in this loop. Okay, so just an inductor and a capacitor, LC, with no resistance. So what's going to happen? We need to make a few definitions and conventions. So let's say that I'm going to define the direction of positive currents to be counterclockwise around this loop. Counterclockwise current will be positive. And I'm also going to define the charge on the top plate of this capacitor to be little q. So little q could be positive or negative in principle. We see that based on the way the capacitor is hooked up to the battery, that initially little q is going to be positive when we are initially fully charged up. And if that's the case, then a positive current would be delivering more positive charge to that top plate. So the charge Q and the current are related this way. A positive current will be increasing Q by adding more positive charge onto that top plate. So I is dQ dt. Okay, at time zero, initial Q is big Q. We'll call it the initial max value of our capacitor. It starts out fully charged. And at time zero, there is no current through our branch here. I initial is zero. Let's now write down our Kirchhoff equation from our Kirchhoff-Maxwell law for this loop here, going counterclockwise around this loop. So going in the direction I've defined as the direction of positive current. Okay, if we started here, then we'd be going with positive current through our inductor. So that's minus L di dt. Then we'd be going with positive current through our capacitor from plate Q to the other plates. So we'd be going down in potential if Q is positive. So that's a minus Q over C. That's the potential difference we're encountering as we go across our capacitor. And that gets us back to where we started. No resistor, no battery in this loop. So that's our full equation. And if we just rearrange a bit, we can see how the rate of change of the current is going to depend on the instantaneous charge on that capacitor plate. So for instance, at time zero, when our initial charge is positive, if this is positive, then the rate of change of current is negative. Now, the initial current is zero, so the current is zero, but its derivative is non-zero. Its derivative is going to be negative at that initial time. So let's start working on a couple of graphs here of the charge on that top plate, Q versus time, and the current in our loop, I versus time. From the moment we throw that switch and allow our capacitor to start discharging through this loop here. So, okay, time zero, we note that our initial current is zero, but we also see here from our Kirchhoff law that the derivative of the initial current is going to be negative. So, negative derivative there at the beginning. Our initial charge is positive here, but if our initial charge is positive, then let's see, the rate of change of that charge is going to be equal to our current. And our initial current is negative, so our initial current is zero, so dq dt is zero at the beginning. So our dq dt, our initial slope there, is zero. So a negative initial slope here and a zero initial slope there. What's actually happening? This top plate has a positive charge on it, but when we throw that switch this way, now there's a path for that positive charge to move around to the plate where the negative charge is. So that's exactly what's going to start to happen. Current is going to start to flow clockwise through our loop here as the capacitor discharges, as this positive charge moves around this way to the other plate. So our initial current is going to be against the direction we've defined to be a positive current. So our initial current is going to be negative. That's what we're seeing here. Well, initial current is 0, but it's about to become negative. It's about to become clockwise. So I'll note down here that negative current means clockwise, and a positive current means counterclockwise based on our definitions in this case. So if charge is leaving this top plate, then Q is going to be decreasing over time. So as we allow time to go on, Q is going to be decreasing as this top plate discharges. But as long as Q stays positive here, di dt stays negative. So this stays negative here, and our current is the rate of change of our charge. So this derivative here is negative, so our current is negative, and the derivative of our current is negative. So our current is doing something like that. We're getting an increasingly clockwise current. The current is speeding up, increasing in magnitude, going clockwise. Now, this takes time to develop because of the electromagnetic inertia in our inductor here. So our current starts at 0 and is gradually building up in the clockwise direction as we move more and more charge from that top plate to the bottom plate. So a time will come when we have moved all the positive charge off of that top plate, when Q here goes to 0. Once all the charge is moved from the top plate to the bottom plate, then both plates will have 0 charge, or both plates will be neutral. So a time will come when the charge on our top plate goes to 0. And at that time, when the charge on our top plate goes to 0, di dt will have gone to 0. So at that time, we're going to have a 0 derivative. We'll have reached a minimum down here in our current. Let's see if I can just sort of line up these moments here. This is the moment when our capacitor is fully discharged. Q has gone to 0. That is not going to be the end of our story. The capacitor is fully discharged, but our current at this time has reached its maximum, or like the magnitude of the current has reached its maximum. So we've been discharging the capacitor, but now we've finally built up a big clockwise current. And if there's a big current going through that inductor here, that inductor has a vested interest in keeping that current going. The electromagnetic inertia represented here is going to try and keep current going clockwise. So even though we've discharged our capacitor, that current is going to keep flowing. And if that current continues to flow clockwise, even though this plate here it has 0 charge on it, if the current continues to flow, if we continue to remove positive charge from that plate, then Q is going to go from 0 to being negative. We're removing more positive charge. Now this Q is becoming negative, and if we're delivering that positive charge to the bottom plate is going to start becoming positively charged. So it's kind of like we discharged our capacitor, but we've overshot our goal. Our current is still removing charge, still moving positive charge from the top plate to the bottom plate. And so our charge on that top plate now starts becoming negative. And once the charge on our top plate becomes negative, then di dt becomes positive. So our derivative turns around, and our current, while still clockwise, is now gradually decreasing. This inductor is going to try and keep the current going clockwise, but it can't keep it up forever. So our clockwise current is now diminishing with time. And so the time will come when our current does go to 0. And when our current goes to 0, at that time dq dt will be 0, so our charge will be at an extremum here. So at this moment, let's line them up. This moment, what has happened? We have taken all the positive charge that was on the top plate, we moved it to the bottom plate. So the capacitor was negative. Sorry, the capacitor was neutral, but then that was here. But then we kept on going, moved a bunch more positive charge from the top plate to the bottom plate, making our top plate negatively charged. In fact, we will have reached a charge on the top plate that's equal and opposite to our initial charge. We've completely reversed the polarity of our capacitor. Now our top plate is negative, our bottom plate is positive, and we've recharged the capacitor. We were trying to discharge it, but we overshot and ended up recharging it with the opposite polarity. So now we're kind of like back at our initial state. The current has gone to zero, and we have a fully charged capacitor. But of course, that's not going to be the end. There's no current now, but this capacitor with all its positive charge, this plate here with all that positive charge is going to want to travel back around counterclockwise to get to that negative plate, and so that's going to begin to happen at this point. Let's see. If Q here is negative, then di dt is still positive, so our derivative here is still positive. Now our current is going to start going counterclockwise. And if we've got that counterclockwise current that's now positive, then dq dt is now positive. So this turns around, and we see what's going to happen. This capacitor, which is fully charged with the reverse polarity, is now going to discharge counterclockwise until it reaches zero charge again. And our current will have grown to its maximum value in the counterclockwise direction. And at that time, we fully discharged our capacitor again. So both here and here, fully discharged capacitor, but we've got a current going. Now there's a big counterclockwise current going through that inductor. That inductor is going to keep that current going. So it's going to continue to deliver positive charge to the top plate. So it's discharged, but we're sort of overshooting that mark and charging up our capacitor all over again. Charging up that top plate. Current will decrease based on these two derivative relationships. These are really our keys to our understanding, there and there. And we're seeing what looks like a kind of oscillation here. It looks like we've gone through a full cycle. We started with a fully charged up capacitor, discharged it, recharged it with the opposite polarity, discharged it again, and then recharged it back to the original state. And our current has gone from clockwise to counterclockwise. Our current has flipped directions and grown and shrank in magnitude throughout this full cycle. And we can see how now it's just going to repeat. Could we have expected this behavior? Let's take a look back at our Kirchhoff-Maxwell loop equation here, this equation. Let's see, if the current is dq dt, and here we have the derivative of the current, then ddt of the current will be the second derivative of charge. So di dt equals d squared q dt squared. And if we write it like that, this equation here, with this replaced with d squared q dt squared, then we've got that second time derivative of the charge on the top plate q equals the opposite of some constant times our charge q. And that we recognize as having the form of a system that undergoes simple harmonic motion. Whenever we find an equation of this format, when the second time derivative of some variable equals the opposite of a constant times that variable, then the solution for that variable as a function of time will be sine and cosine functions, where this constant ends up becoming our angular frequency omega, or that constant squared, that constant is omega squared. Omega is our angular frequency for our oscillation here. So we recognize that this constant, the 1 over LC, this must be our omega squared, 1 over LC. Based on comparing the dimensions, on this side we've got charge over time squared. So this is charge, so LC must have units of time squared. An inductance times a capacitance is apparently equivalent to a time squared. So omega squared is this, and we see that what we've got here is indeed a simple harmonic oscillator. We've got an electric circuit that oscillates. And the period of oscillation has now been determined, 2 pi over omega, so 2 pi times the square root of LC. So here is your sort of LC time constant here. LC is not a time, LC is a time squared, and in fact 2 pi times the square root of LC, that's the period of our oscillation. So this time right here would be capital T. This time right there is capital T. That's one full period. So that amount of time is 2 pi times root LC. We do indeed have sine and cosine functions here. Let's write those functions down. We see here that in this particular case, since we started with a fully charged capacitor, Q of T equals big Q cosine omega T. And our current is, of course, the derivative of that function. So it should be a minus sine function, which is exactly what we've ended up drawing here, a minus sine function. So I of T is dq dt. So minus, let's call it capital I for the max value of I. This is our max current, just as this is our max charge on the plate. And omega is given by this right here. Okay. So what we found is oscillatory behavior in our circuit as our circuit sort of discharges this way and then reverses and runs current this way and then reverses again and again. And if our circuit is ideal with no resistance in here, then this oscillator continues to oscillate in this fashion forever. This is the basis of many technologies, particularly with radio technologies. This can become the basis of a resonator. Let's talk next about the energy involved.